Okay. This video will be slightly smaller than usual. I just want to give you some time to enjoy your uh, post-exam stress relief, I guess. Okay. We'll cover some ideas of cryptography, of CPA encryption and some examples. And we will discuss the proof of the algorithm that we saw last time is actually CPA, secure encryption. Okay. So last time we generated um, algorithm, and we said that, oh, this is CPA secure, and we did not give a proof. Let me just give you a reminder of what the algorithm was. So let f be a length keyed length preserving function, be a length well, be a length preserving preserving keyed function. Okay, and the encryption algorithm worked as follows. We feed the generator a key 1 to the n, which is just 1 1 1 1 1 1 n times, so that it knows what n I am looking at. Okay. It chooses a uniform key form key k, which is of length 1 to n, length n in that case. Right? What does the encryption do? Encryption k of m, in this case, where m has to be equal to length k, for m is equal to k, works as follows. Choose a uniform vector k, choose a uniform r, uniform, choose uniform, should be choose, and uniform uniform r in 0 1 to the n, which is called either the initialization vector or nonce vector. Nonce slash initialization vector. Okay, so I am going to call it nonce vector, but that is what it's like. It's a uniform R separate from your key, and then you output the text, output ciphertext R comma fk R XOR sum m. Okay, how does decryption work? Decryption k of c1 comma c2 gives you output c2 XOR sum fk of c1. Right? So as long as both the sides know the key, this is going to be perfectly valid, and this is easy to check that it is correct. Correctness is immediate. Okay. In terms of picture, if we want to draw a picture of what is happening, it looks something like this. Message is being sent. It is encrypted, and we have a ciphertext, right? But the ciphertext is now of 2 blocks. Ciphertext. The second block is some encrypted is the message of the encryption, which depends on the message, But there's another block, which is the R that is being sent, and that has nothing to do with the message. Right? How is the message being encrypted? It is encrypted using a pseudo-random function. Pseudo-random function. But what does the pseudo-random function take? Well, it takes first an F and the R, right? Which we are sending here. Okay. And the key determines this function's key acts on this function to give the pseudo-random function fk that we'll be using. Okay, so this is just a diagram to give you a picture of what is happening. And we concluded last time that this system is actually secure. We said theorem. If f is a pseudo-random function, is a pseudo-random function, then this scheme is CPA secure. Then this scheme is CPA secure, right? And we had proven previously that such a scheme, if it's CPA secure, then it's multiple message secure for CPA, right? So note, here again, the key has to be as long as the message. The key is as long as the message. But the same key can be used to safely encrypt multiple messages. But the same key can be safely used to encrypt multiple messages. In fact, what that means is if your message is not exactly length n, which is your predefined key, what you could in fact do is break it into parts, each of length n, pad it up so that everything is a multiple of n, maybe with 1 and then zeros, okay? And then encrypt each of these parts with your key, because now they have the same length. They can be safely encrypted, and that will work because this is going to be still secure. Because if it was CPA secure before, under multiple encryption, it is still CPA secure. Okay? Proof. So, by reduction, we're okay. We're again going to reduce the. We are going to reduce. We are going to reduce the problem to an attack on my F. We are going to create a distinguisher D, which succeeds only if my distinguisher. That's right. If my scheme could be broken down, and we will show that because such a distinguisher does not exist, it means that the scheme is secure. I will not present the full details. Full details are in the book. Here is the intuitive picture. We present an represent the the picture here. The picture here. So you might want to keep the book open with you if you want when you're doing this, okay? But the idea is going to be this. There will be a distinguisher D, idea, create distinguisher D, which has access to an oracle O, either random or pseudo-random. What does that mean? The idea is there's a distinguisher D which has access to the oracle. Maybe it has access to two different oracles, O1, O2, doesn't matter. The idea is it needs to figure out whether this oracle is random or pseudo-random. What is the oracle? It uses either function f, uniform function f, uniform function f, or uses fk once the key is chosen. Okay? And how does this one works? How does this distinguisher work? It works by using A as a subroutine. Uses A as a subroutine to attack pi. Okay? So let me draw you a picture and explain in words what is happening. Okay? So I have an oracle O, which is either random or pseudo-random. So pseudo-random or random. We do not know. Okay? And we are querying it with stuff, right? And here's what my distinguisher D is going to do. Whenever the adversary A sends a message, okay? Whenever the adversary A tries to query a message, what it does is, oh, okay, A is sending a message M, right? It first chooses a uniform bit R from 0, 1, okay? And it sends R to my to my oracle O and gets the function fr. Okay, now fr, if the oracle was random, is going to be a actually random function uniformly chosen. If it's only a pseudo random, then it is going to be fk of r for some k key which is chosen before. Okay. Now what do we do with this fr? Well, as per my encryption system, what it's going to do is it is going to XOR M with this, okay? And then give the output as R, comma, FR and M to my A. Okay? And now output 1 if A succeeds, um, sorry, this is how D acts as an encryption oracle. D acts as the encryption oracle for A. Now D acts as encryption oracle for A. Okay. Now, how do we set up the experiment? The experiment, we want D to be distinguishing whether my oracle is random or pseudo-random based on what A does. And the experiment is going to be as follows. We again have basically the same setup. The oracle O that D wants to figure out whether it's random or pseudo-random. And my distinguisher D doing the more or less same thing as before, except now since it's part of an encryption, A has to give two messages, M0 and M1. Okay. What do? You choose a bit first, between 0 and 1, and then you again choose R star, okay, which now is exactly the same as R. Its job is same as R. It is again chosen uniformly. Oops, maybe at the wrong place. R star is chosen uniformly between 0, 1, as a 0, 1 to the n string. It is fed to the random oracle, and the random oracle or pseudo-random oracle is going to output FR star, right? So maybe I will draw the lines like this. So you get an FR star from the random / pseudo-random oracle. You encrypt the message MB that you chose, one of the two, right? And then you send this ciphertext to A, which is R star, comma, FR star XOR MB. Okay. And then, okay, let me just draw this a bit better. MB. You're sending it, once you finish encryption, you send it the ciphertext or challenge text in this case, R star FR star MB. Oh, sorry, FR star XOR MB. Okay. And finally, A outputs bit B prime. Okay. Now, what do you do with this output? If B is equal to B prime, output 1. Okay. This is what my distinguisher D is going to do. Okay. With my adversary A. This is the experiment that D is going to run. Note that since A runs in polynomial time, so does D. As A runs PPT time, polynomial time, probabilistic polynomial time, so does D. Because while D is doing some extra steps, the steps by themselves are finite. Like there's a small number of steps. It's not an exponential number of steps that it's doing. It's doing 4 more, 5 more steps. Okay? There are some extra steps that are being done, which are queries to the oracle O and queries that A does to D. Right? Now, because A runs in polynomial time, it can only make polynomial many queries to D. Okay? So let mu n is equal to, just for what do you call it? Just for ease of notation, let this be the probability that the experiment succeeds for any length n. Okay? And let Qn be a bound on the number of encryption entries made by the attacker. Be a bound on the number of encryption queries made by A. And as we mentioned, at most polynomial as A is a PPT attacker. PPT attacker. Okay. So now let us look at what is happening. Okay. If F was pseudo-random, if F is equal to Fk, which is a pseudo-random, for some uniformly chosen key, uniform k, then the view that the adversary, in the view of the adversary A, things are happening exactly as the experiment CPA experiment A pi. Then the view of A is exactly same as in private encryption experiment CPA A comma pi of n. Okay. And so the chance of success, since I am saying that, oh, I will succeed as, whenever this experiment succeeds, is going to be the probability that k 0, 1 to the n dfk is equal to 1, the same as probability of the experiment succeeding under CPA and is equal to 1, which we said is mu n. Okay. Now, if instead f was uniform, then we have to take a look at two subcases. if F is uniform, there are two subcases. Okay, what are the two subcases? R star was never used before, okay, and R star was used before. So let's consider the first case as R was used, R star was never used before, was not used for some other ciphertext that we queried before, because A can make polynomial many queries, right? A made QN queries to, what do you call, to RD encryption oracle, to figure out things, get encryptions of messages M that it desired. If the R star was never used, then we are in the first case. But since they are chosen uniformly and randomly, there is a chance that it might show up. It might have showed up before. So that's R star was used for some other ciphertext. Was used for some other ciphertext. Okay, so we'll call this case as not repeat, and we'll call this case as repeat. Okay. Okay. So in that case, the probability that my experiment succeeds um, is exactly equal to probability of F, that dF is equal to 1, is actually, this is smaller than or equal to, this is exactly equal to probability F that dF was equal to 1, given that R star was not repeated. Okay. Plus probability that F dF was equal to 1, given that it did repeat. Okay. And now comes a little flaw in the argument. Okay. Not exactly a flaw, but maybe a catch. What is happening is when my key is repeated, so PRF D F.1, given that repeat case is happening, is we can say this is smaller than or equal to the probability that the repeat is happening. Okay. And the major reason for this is that if um, if R is repeated, sorry about that. If R is repeated, then what is happening? In a query that you made, R was repeated. While you don't know while you don't know your what do you call? While you don't know your key K exactly, right? There is no exact key K. So your ciphertext that comes out is going to depend exactly on R and FR and your message M, right? And in that case, it is possible to figure out what FR star was. Okay? And it is quite easy to succeed in breaking the system if R was repeated. Okay? Mm. Quite easy to succeed. Quite easy to succeed. If if R repeated. Okay? So in that case, you can more or less say that, oh, every time it repeats, my experiment will succeed. I don't need the extra condition that df is equal to 1. um, sorry. This should be and, not given. And, okay. And the thing was repeated. Because the probability of this is probability of it repeating, of the experiment succeeding, and it was repeated is probability of experiment succeeded, given that it repeated multiplied by repeated. And so we can say this is safely smaller than or equal to. Okay? And so, therefore, I can say the probability of f, given that the f0 is equal to 1, is equal to probability that it did repeat did I make mistakes on it? Ah, yes, that's fine. Probability that it did repeat plus probability that the experiment succeeded, knowing that it did not repeat. Okay, oops, sorry, this should not be equal, this should be smaller than or equal to. Okay, now the question is, how many times does the case happen that the experiment that R was repeated? Well, we made q to the n queries, right? And the total number of R's possible is 2 to the n. So the probability of this happening is q of n over 2 to the n. And what is the probability of success if R did not repeat? Well, if R did not repeat, you're just making blind guesses, right? So you can say that you're succeeding or failing about half the time, because that is how much it should be. Okay? Since f is pseudorandom, pseudorandom, the first condition is that mu n should be sorry, probability, not FR. Probability for a uniform case d f is equal to 1, this should be smaller than or equal to some epsilon n for some negligible function epsilon n, right? Which means that mu n should be smaller than or equal to the probability of success of d to the f is equal to 1 plus some epsilon n, negligible function, right? Which is to say, well, I already said that this is smaller than or equal to 1/2 plus q of n over 2 to the n plus another epsilon n, right? And now, because qn is polynomial, right? At most polynomial, qn over 2 to the n is also negligible, right? And therefore, probability of the private key experiment under the CPA experiment, a pi n is equal to 1, which is exactly mu n, as we defined before, is smaller than or equal to 1/2 plus some other epsilon prime of n, which is also a negligible function. And hence, it is actually computationally secure. Okay? So I am glossing over some of the details. I'm not going over full, complete details of the proof. Okay? You can read the book. This is given in full details in the book. You might find it helpful to read it at least once. Okay? So therefore, the system is secure. What happens in real world? Real world security. Okay? Well, I showed that computationally it's secure, great. What happens in the real world? Is it good or bad that it's computationally secure? Well, we have shown that the security bound is tight. We have shown that there is an epsilon prime of n, which is still a negligible function. The bound we proved is tight. Okay? Okay? And in fact, uh, we might not ever use Rn twice, right? So there are some things that have to be taken into consideration. We might actually be doing better or worse depending on certain things. What happens? What happens if a nonce vector R is ever reused? Maybe not for the same exact messages right now, but later. What happens if I'm using it again? Right? What is the probability that? What is probability that the nonce used in some challenge ciphertext, some challenge ciphertext is also used for some other ciphertext? Other ciphertext. And what happens to the bound? What happens to the bound if the nonce is chosen non-uniformly? If the nonce is chosen non-uniformly, maybe pseudo-randomly. Okay, of which the third one sounds the worst one, right? But these are questions that do pop up in real world. Um, Uniform data isn't available for everything. We often use pseudorandom exactly for that. And these are the drawbacks in real life. But we don't have to worry too much about it. Um, because for now, we are not really worrying about real life. We are worrying about a first course in Introduction to Cryptography. This is not real world cryptography that we're using cutting edge cryptography. So for now, we are focused only on the theoretical, the CPA, secure encryption, So we have shown that a CPA secure encryption um, is secure as long as we have a pseudo-random function, right? We have shown CPA secure encryption encryption scheme based on any block cipher with a pseudo-random function, right? What is a block cipher? We are ciphering a block of length n. Encryption k of m is of kr. So as we have discussed before, there are two ways. One is stream ciphers and one is block ciphers. We are using block ciphers, which are defined length n. We have to choose the length n, and only then we are doing things. Okay. What are the major drawbacks of this, however? Well, a one block plain text, plain text, just became a two block ciphertext. Becomes a two blocks ciphertext. Okay. Frankly, which is quite annoying. It's effectively doubling the size that you are sending in terms of bandwidth, in terms of storage, in terms of everything. It's quite annoying to have doubled in size, right? And the other problem is only defined for encryption of n-bit messages. For encryption. Once again, because everything is because my f is keyed, length preserving, everything only holds for n-bit messages. My keys have to be sent out first. I cannot change the length of my message afterwards. Okay? So that creates a very big problem. I don't want to encrypt only encrypt messages. What if I want to encrypt longer messages? So encrypting long messages. How do we encrypt long messages? And the good news is, recall that CPA secure actually means CPA security implies security of multiple messages. Multiple messages. And so what we do is encrypt a message. So can encrypt a message message m is equal to m1 m2 mt as encryption of m1 encryption of m2 encryption k of mt. Okay, and this is also going to be CPA secure. Okay, and there are multiple ways of doing this. Okay, however, what is the major drawback? Drawbacks. The single biggest drawback that we have talked before is that the length of the ciphertext is twice the length of plaintext. Of ciphertext is twice the length of the plaintext. Right? So the question becomes, can we do better? Can we do better? And the answer is yes. Okay, there are various modes of doing this. Yes, via various modes. Okay, let us first see something that is not that does not work. Electronic book mode. Electronic code book. Sorry, code book. ECB mode. Okay. So the naive way, the super easy way that we could think of is saying that, oh, I need, instead of saying that, oh, I'm going to repeat a parameter r every single time, I'm going to find a new parameter, and that is effectively doubling my length. What if we encrypt everything using the same parameter r? Encrypt everything with same uniform r. Okay. And so my ciphertext C in that case is going to be, well, R, I'm probably going to look like R, and well, something related to fk of m1, fk of m2, and so on. Dot 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 fk of mt, right? And here's the very, very big problem. This is deterministic. Deterministic once R and K are chosen. Okay, which means this is not CPA secure. Not CPA secure. URE. In fact, if if a message block is repeated, we can tell from a ciphertext that two blocks are repeated. Can tell from ciphertext if mi is equal to mj, which means it's not even EAV secure. Therefore, not even EAV secure. C U E. Therefore, big no. So never use this. Never use this. Okay. This is a terrible method, and we are looking at it only for historical importance. This was thought of initially, and it is one of the first things that you can think of, which is why it's important. But it's a terrible method of encryption. Okay, never, ever, ever use this. A better method is, for example, the CBC method, which stands for cipher block chaining. Second, cipher block chaining. CBC mode. Okay. So how do we change? How do we do it in CBC mode? Well, suppose you are encrypting M1 to MT, where T is random. Okay. The idea is this. First, choose your random R and call it C0. Okay. 0, 1 to the n, also called IV. Think initialization vector. Okay. What we call the nonce vector, the same as initialization vector. Generally, the book refers to it as initialization vector. Okay. And now, what you do is, for I is equal to 1 to t, you say that let's see I is equal to fk of mi XOR ci minus 1. Okay. And so your output is output ciphertext C is equal to C0, C1, CT. Okay. A limitation on this, a slight limitation, is that it requires F to be invertible. Requires F to be invertible. But the great news is, it is just expanding the ciphertext by one extra block, which is C0. So ciphertext expansion is just one block. Right? Rather than n blocks, the same number, this is one block. Okay, I'm not going to prove that this is secure, but for now you can try. You should just assume that it is. Okay. So in terms of an image, and just to help you visualize what is going on, M1, 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 FK, C1, check your output, encrypt M2, hit it with FK, output C2, MK, FK, CT, so MT, not F, MK. MT. Okay. And the theorem says if F is pseudo-random permutation, if F is a pseudo-random permutation, i.e. F is a one-to-one function which is invertible, then CBC mode is CPA secure. Is CPA secure. Okay. The problem with this is that it has to be done in order. You have to decrypt. In terms of decryption, you first have to find out C1 as C0, use that to decrypt C1, use that to decrypt C2, you use that to decrypt Cn, and so forth, right? You cannot do them parallelly. So if you have, for example, multiple cores processing and everything, this is not the most efficient use of your multiple cores. You can't do Ci and Cj at the same time. The one that you have done first has to be done. You have to be doing that at one time. Okay. Compared to that, what is called is the counter mode. Counter mode. Okay. So counter CTR mode. Oh shit, I said that it will be shorter. This is also pretty long. Well, okay. Uh, sure, I won't prove this one right now then. Okay, the counter mode. How does this work? Well, again, you want to encrypt, say M1 to MT, where T is again arbitrary. The first thing you do is choose the initialization vector, uh, again, and call it CTR as your counter, and you set C0 is equal to CTR. Okay. Now, for I is equal to 1 to T, what you can do is you use Ci is equal to Mi XOR Fk of CTR plus I. Okay, where this is modulo 2 to the n. So it's a bitwise sum, not a bitwise sum. What do you call? You can think of them as members of mod 2 to the n. Take the sum, use them. Okay, and then output C0 to C0 C1 dot 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 CT. Okay, and this is much easier, and decryption is more or less straightforward, and it can be fully parallelized. Okay, decryption is then going to be mi again, mi is equal to ci, sorry, fk ctr plus I. Okay, can be fully parallelized. Can be fully parallelized. Okay, and once again, the ciphertext expansion is just one block. Ciphertext expansion is just one block. So in terms of an image, you have CTR, which you're setting as C0, CTR plus 1, hit it with FK, XOR it with your message M1 to get C1. So let me just make all of these the same length. CTR plus 2, hit it with FK, XOR with message M2, get C2, dot dot dot, CTR plus T, hit it with FK, XOR with MT, get CT. Right? And the theorem. This is actually secure. If f is a pseudo-random function, random function, then the CTR mode is CPS secure. And I won't give you the full proof because I wanted to keep this short. Proof sketch. sketch, TCH, sketch. What happens is the sequence fk of ctr I plus 1 dot 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 fk of ctr I plus t used to encrypt the ith message, to encrypt the ith message is pseudo-random. This pseudo-random. Okay. So moreover, it is independent of every such other sequence. It is independent of every other such sequence unless ctr of I plus j is equal to ctr of I prime plus j prime for some I j I prime j prime, and so you have to bound by the probability of the event. Bound by the probability of this extra event, which, as it turns out, is negligible in n. Okay, the proof in full terms is in theorem 3.32 in the book, so you can go through it. Okay, but for now, let's stop this one here.